Hi, everyone. My name is Nick. I am working at Queen's University in Kingston, and this is my presentation on the evaluation of flight parameters in UAV-based 3D reconstruction for rooftop infrastructure assessment. All right, so if you've been to any other inspection presentations so far, you've probably already heard this, but traditional inspections typically involve rope access, which requires training, which is expensive and time-consuming, or it involves boom trucks, hydraulic lifts, and other mechanical equipment, which is expensive to rent, and also requires shutdowns of the infrastructure. Inspections are also subjective because they rely on one inspector's opinion on what is relevant to be captured, and they're difficult to quantify over time. So if you have an infrastructure report from 4 years ago, it might contain images of different items versus a report today, and it's difficult to quantify any changes between these different reports. So with the innovation of new technology, some of these pitfalls have been mitigated. So with UAVs, UAVs are able to access different areas that aren't available for manual inspection. They also cut down on time and require workers to be in less high-risk situations. However, this still doesn't kind of address some of the issues with a global visualization of the structure and capturing things over time in a repeatable, consistent way. So this is where 3D reconstruction can come in. So creating a 3D model of a structure, basically a digital twin that can represent the structure over time and can be inspected offsite for defects and any inspection requirements. However, as you can see on the right there, flight parameters are critical. If you don't have a high quality model, then it's kind of useless as a representation of the structure. So that kind of brings me to the objective of this research, which is how to optimize UAV-based photogrammetry for rooftop inspection by identifying flight parameters that minimize data collection while also maintaining high 3D reconstruction accuracy. So just to overview kind of the different standards in the industry right now, there's kind of 3 levels of autonomy. So you have completely manual flight, where you have an inspector flying the drone completely manually, taking images wherever they think is necessary. So this comes with some advantages, minimal pre-planning, and no additional proprietary hardware or software besides the actual drone itself. In terms of disadvantages, this can be time-consuming and requires an inspector to be manually flying the drone the entire time, and it has poor repeatability or consistency, just like a manual inspection. The area I'm going to be focusing on in this presentation is pre-planned flight paths. So this is highly repeatable. You can simply program a set flight that you can repeat on the same structure or repeat the same parameters on different structures. However, limitations are to the quality of the reconstruction, which is what we're going to be investigating, and the requirement for pre-planning. Finally, we have a fully autonomous flight. So this comes with some advantages and disadvantages as well. So it's highly adaptive to the task and minimal pre-planning. You just set the drone down and it conducts a flight by itself, but this requires proprietary hardware and software that can be expensive and difficult to obtain. So just going over the flight parameters that we were using a double grid Boströmvinden pattern, which is basically just like a lawnmower pattern going in 2 directions with an oblique camera angle. So this basically gives us 4 directions on any item in the scene, and it's just the industry standards. That's what we used. The 2 parameters we were measuring or varying were ground sampling distance, which is basically the resolution of the real life structure in the camera. And this basically varies on camera parameters and the elevation of the drone flying overhead. And then also image overlaps. This is literally just the overlap between each image of your flight. And so what we needed was a way to evaluate our models compared to a ground truth, right? We wanted a way to quantify how accurate our model actually was compared to the real structure. So we did this through point cloud comparison. So we established a ground truth, which I'll get to in a second. And then we used 3 different criteria to evaluate this. So we used precision, recall, and F-score. These are just industry standards for evaluating 3D objects. But basically, precision identifies the accuracy of the model. So the cloud-to-cloud distance of every point in the model relative to the ground truth, and it's expressed as a percentage of points that pass a certain threshold. Recall is kind of the opposite, so it measures the completeness of the model, measuring every point in the ground truth relative to the model. And F-score is kind of a holistic metric that covers both of these things. So F-score is kind of the main one we're looking at in terms of a complete view of the accuracy of the model. So here you can see an example of a scalar field for the precision and recall on a structure. So highlighted in the scalar field is the cloud-to-cloud distance, And you can see yellow, for example, is high error. So you can see there's an area of deformation on the top roof, and that's expressed with yellow there. All right, so the next step was establishing a ground truth model. So our model consisted of two main items. So one of them was the DJI Matrix 350 RTK with a DJI Zenmuse L2 LiDAR platform. The downside with this is that it's dependent on IMU calibration and GPS and RTK sent signals. So we weren't 100% confident that it was going to be reliable throughout the whole reconstruction. So we validated it with a second system, which is a ferrofocus terrestrial laser scanner. This was highly accurate and had a high point cloud density, but it was infeasible to do over the entire rooftop structure. So what we did was we measured the F-score in three different high geometry areas to identify that the drone-based LiDAR was reliable. And it was had an F-score of 85% or higher across a 2 centimeter threshold for all three of our areas. So going forward with that, we were able to use the drone-based LiDAR platform to validate. And here's our experimental setup. So our main site was one building on Queens campus here, and we divided the roof into 5 sections. This is so that we could identify how lighting, elevation, obstruction, and rooftop items were able to influence the reconstruction quality. And here we came up with a matrix of 9 flights where we were able to vary our ground sampling distance and our overlap, and then identified our 3 kind of cost criteria to measure the efficiency of the flight. So looking at the results, when you have high levels of error, it was pretty obvious. You could just see from qualitative observation. This is just varying ground sampling distance, and as you can see there's areas that show significant difference in terms of quality there. But as the accuracy increased, it became more difficult to visually see the error, and that's when we turned to the F-score to provide a qualitative analysis. So this is kind of the example you'd get is like a scalar field for your precision and recall, and then different threshold values as percentages over a specified distance. So here were our final results, the F-scores for the different flights across the different roof sections. So as you can see, the middle ground sampling distance, which is 0.75 to 1.26, provided the highest accuracy, with green being the highest F-score and blue being the second highest. And then flight 6 and 7 here were the higher overlaps in this area, and they produced most of the highest quality models. Just looking at some specific results for the different roof sections, for complex roof sections, which are A and B, we were able to see that the low overlap had significantly poorer results here. You can see in the graph. And generally, the other ones were pretty close together at all threshold levels. When looking at the flat roof section, they also stayed very close together. And even with the low overlaps, most of them performed well besides one. And I'll kind of get to the implications of that later. And then for the low roof sections, this is where we had the most variation between them. So the higher GSD, so higher elevation drone flights, performed significantly worse on these kind of obstructed, darker areas. And also the low overlap obviously performed poorly as well. So kind of the main takeaways from this, we were able to identify kind of the optimal parameters for overlapping ground sampling distance. So we identified that 85% was the most effective overlap, and then above that we saw diminishing returns, and flights at this GSD here provided more accurate reconstructions. And then some additional observations. For low complexity geometry, like our flat roof section, even lower overlap can still yield effective results, but there was lower cost criteria associated with that. And then fine details weren't captured even at the optimal overlap in GSD. So if you're looking to really capture thin railings or fine-walled surfaces, you may need manual flight to supplement your reconstructions. And then finally, regardless of GSD and overlap parameters, the lower roof sections performed worse. So if you have areas of high obstruction or low lighting, you may need manual flight or even additional manual captures in person to better improve your reconstructions. And that's everything. Thank you for your time.